friction is the force resisting the relative motion of solid surfaces, fluid layers, and material elements sliding against each other. There are several types of friction. Dry friction resists relative lateral motion of two solid surfaces in contact. Dry friction is subdivided into static friction between non-moving surfaces, and kinetic friction between moving surfaces. Fluid friction describes the friction between layers of a viscous fluid that are moving relative to each other. Lubricated friction is a case of fluid friction where a lubricant fluid separates two solid surfaces. Skin friction is a component of drag, the force resisting the motion of a fluid across the surface of a body. Internal friction is the force resisting motion between the elements making up a solid material while it undergoes deformation. When surfaces in contact move relative to each other, the friction between the two surfaces converts kinetic energy into thermal energy. This property can have dramatic consequences, as illustrated by the use of friction created by rubbing pieces of wood together to start a fire. Kinetic energy is converted to thermal energy whenever motion with friction occurs, for example when a viscous fluid is stirred. Another important consequence of many types of friction can be wear, which may lead to performance degradation and/or damage to components. Friction is a component of the science of tribology. Friction is not itself a fundamental force. Dry friction arises from a combination of intersurface adhesion, surface roughness, surface deformation, and surface contamination. The complexity of these interactions makes the calculation of friction from first principles impractical and necessitates the use of empirical methods for analysis and the development of theory. History. The classic rules of sliding friction were discovered by Leonardo da Vinci, but remained unpublished in his notebooks. They were rediscovered by Guillaume Amontons. Amontons presented the nature of friction in terms of surface irregularities and the force required to raise the weight pressing the surfaces together. This view was further elaborated by Bellador and Leonhard Euler, who derived the angle of repose of a weight on an inclined plane and first distinguished between static and kinetic friction. A different explanation was provided by de Sagaliers, who demonstrated the strong cohesion forces between lead spheres of which a small cap is cut off and which were then brought into contact with each other. The understanding of friction was further developed by Charles Augustin de Coulomb. Coulomb investigated the influence of four main factors on friction: the nature of the materials in contact and their surface coatings, the extent of the surface area, the normal pressure, and the length of time that the surfaces remained in contact. Coulomb further considered the influence of sliding velocity, temperature and humidity, in order to decide between the different explanations on the nature of friction that had been proposed. The distinction between static and dynamic friction is made in Coulomb's friction law, although this distinction was already drawn by Johann Andreas von Segner in 1758. The effect of the time of repose was explained by Muschenbroek by considering the surfaces of fibrous materials, with fibers meshing together, which takes a finite time in which the friction increases. John Leslie noted a weakness in the views of Amontons and Coulomb. If friction arises from a weight being drawn up the inclined plane of successive asperities, why isn't it balanced then through descending the opposite slope? Leslie was equally skeptical about the role of adhesion proposed by de Sagaliers, which should on the whole have the same tendency to accelerate as to retard the motion. In his view, friction should be seen as a time-dependent process of flattening, pressing down asperities, which creates new obstacles in what were cavities before. Arthur Morin developed the concept of sliding versus rolling friction. Osborne Reynolds derived the equation of viscous flow. This completed the classic empirical model of friction commonly used today in engineering. In 1877, Fleming, Jenkin and J. A. Ewing investigated the continuity between static and kinetic friction in the paper on friction between surfaces moving at low speeds. The focus of research during the last century has been to understand the physical mechanisms behind friction. Philip Bowden and David Tabor showed that at a microscopic level, the actual area of contact between surfaces is a very small fraction of the apparent area. This actual area of contact, caused by asperities, increases with pressure. The development of the atomic force microscope has recently enabled scientists to study friction at the atomic scale, showing on an atomic scale dry friction is the product of the intersurface shear stress and the contact area. These two discoveries explain the macroscopic proportionality between normal force and static frictional force between dry surfaces. Laws of dry friction. The elementary property of sliding friction were discovered by experiment in the 15th to 18th centuries and were expressed as three empirical laws. Montan's first law. The force of friction is directly proportional to the applied load. Montan's second law. The force of friction is independent of the apparent area of contact. Coulomb's law of friction. Kinetic friction is independent of the sliding velocity.